chaining and garbage collector. We have seen that constructor chaining. Okay. Constructor chaining is the process of calling one constructor from another. This happens in two ways within the same class using this between parent and child classes using super. This one is important. We will cover this in detail in our inheritance chapter. Okay, so you can skip this for now. The primary constructor pattern, designate one constructor as the primary, okay, the one with the most parameters, and have all other constructors delegate to it. All right, you can see that. Why not destructors in Java? In C++, you can say the destructor, something like that, is used to manually free memory when an object is no longer needed. Java does not have destructor because we have garbage collector. Okay, automatic garbage collection, the finalize method, and this one is deprecated, so don't focus on that much. Java previously provided this method that ran just before the garbage collector reclaimed an object. It has been deprecated since Java 9 and do not use that. Okay, because its timing is unpredictable and it degrades our garbage collector performance. All right, now our constructor lifecycle summary. So first we have invocation. New class name is called. Okay, then in this tab our Java allocates memory on the heap, and then chaining this or super delegates initialization. This call delegate until a constructor without this is reached and eliminates duplicate initialization logic, right principle. Then we have execution. Constructor body runs. The object state is finalized, and this means our fully initialized object's address is returned to the caller. All right, and after that some operations done and we no longer need or our reference is destroyed, our garbage collector reclaims memory automatically. Okay, and one very important thing is in this chain our object is never accessible until our code finishes this chain completely. This means that we cannot get half built object, and this is one very important safety guarantee of our data integrity as well. Now we have quick summary. You can take a look in this one and we can move to our next chapter, which is static variables. Static variables and memory. In standard object-oriented programming, every call to new creates a fresh set of instance variables, right? And let's assume that we have student objects, 1K student objects, and we have 1K copies of every instance field. Okay, but if all those students share the same university value, storing it 1K times wastes memory, right? So we can solve these kind of problems using static keyword, and our static keyword allows us to create variables that belong to the class itself, not to any individual object. Okay, one copy will be shared by all instances, stored in a completely different place in memory in our method area. Okay, we call that method area basically. Class variables versus instance variables. Instance variables, each object has its own copy. Example, a student's name. And then we have static variables. A single copy shared by all instances. Example, any university name, common to all students. Okay. So in this case, you can see that. Oh, this one is different. Okay. So you can assume something like that, right? Now, memory architecture. To understand static, consider the JVM memory layout. Heap memory, where objects live. 10 student object means 10 separate allocations on the heap, and on stack memory, where local variables and method call frames reside. Okay, then we have separate area, which is method area. We call that metaspace as well, where our class level information is stored, including our static variables, right? Static variables are located in the method area when the class is first loaded by the JVM, even if no object is ever created. And this process is only done once. The shared counter pattern. Static variables are ideal for tracking data across all instances, such as counting how many objects have been created. You can also track that as well. Okay. Something like static int user count, and you can increase here. Okay. So every time this constructor will run, we are basically increasing our static variable value. Every new user increments the same counter. So in this example, user count belongs to the user class. Whether you create 1 or 1k users, there is only one user count in memory. All right. Then we have access convention for that. While you can access one static variable through an object, let's say u1.userCount, always use the class name. This makes it immediately clear that the variable is static to any other developer as well and for any future reading. Okay. It helps your code review, and every professional code base follows this same rule. Then we have quick comparison table, static versus instance. Ownership, instance variable belong to the object, static variable belongs to the class, memory area, heap, method area, created when an object is instantiated, new keyword, okay. The class is loaded by the JVM. Access via object reference, via class name directly. You can access that as well from here, or you can access using instance as well. Okay, this one, but this one is recommended, and always you can see these kind of implementations. Okay, then we have quick summary. You can take a look here, and we can move forward with our next chapter, which is static methods and blocks. So if a variable can belong to the class, so can a method. All right. Static methods perform actions that do not depend on any specific object state. They are commonly used for utility functions and helper logic. We have seen some static methods, right? We have seen from our math utility class, right? Math.max, math.min, something like that. Okay. We also have used in arrays, arrays.sort, something like that. Static methods. The math class in Java is a well-known example. You can call math.sqrt directly on the class without creating an instance. Now we have one very strict rule in case of static methods. Know this rule, okay? A static method belongs to the class, not to any instance, okay? And because of this, it cannot access non-static instance variables or methods directly, right? So let's say you have this class mathutils and you have this one static method square. This can return something here. Okay, int n. All right, that's fine. Static int add, that's fine. Called directly on the class. Okay. So int result math.utils.square, you can pass this value. So no new math.utils required. No new math utils required. Okay, you don't require any instance to call these static methods. One more important thing, let's do one practice here. So let's say we have these instance variables, right? We have one static method. Let's create one static int ab testing. Okay, we can do testing. We can print here something testing. What is that? Missing return statement. Okay. Return one. That's fine. Now, if you try to access something here that is plus username anything, you cannot do that. Non-static field username cannot be referenced from a static context. You will get one error. And the reason behind these things, you already know that because our static variables or methods belong to our class. Okay, and our JVM loads that class in our method area before even any object is created of that class, right? Now, static blocks. Sometimes a static variable needs complex initialization, anything a loop, a configuration lookup, etc. Right? So a static block is a block of code that runs exactly once when the class is first loaded by the JVM, and it executes our code before the main method and before any constructor as well, right? And we call that one time class initialization. So let's say you have this class, okay? You have this static string connection URL. So runs once when the class is loaded, static, and you can do something like that. So our this static block runs exactly once when the class is first loaded by our JVM before even main, okay, before any constructor, before any object exists. It's the class one time setup ceremony. We have one execution order here. When a class is used, Java executes code in a specific order. First, static blocks, and run once when the class is loaded. And if we have multiple static blocks, they run in the order they appear in the source code, right? If we have multiple static blocks here, then they run in the order we have right here. Here, if we have multiple static blocks, they will execute in the same order we have written here. Okay. Second one is instance initializer blocks. Run every time an object is created, run before the constructor. Okay. And these are less common. And in last, we have constructors. Run every time an object is created after instance blocks. Okay. And we can also see one example with these three blocks. In this same example, we can see that. So we have these constructors with chaining, that's fine. We can create one static block here that will run only one time, static block. We can also create one instance block, and that's fine, non-static block, or we can say non-static means that is instance, right? So that's fine. And now let's create two objects just for understanding. Okay, run one, compile one, and so you can see that we have created here two objects, right? But our static block ran only one time, static block, and this is our first statement. Okay, then we have instance block and instance block again, right? So now you can understand properly. Okay, so this will run every time we create one object, and this one will run only one time if we do not create any object. Let's see now, will our static block run this time? Let's see. No. Okay, so our JVM will only node if we have this requirement. That's fine. Now, why use static methods? Memory efficiency, global access, logic grouping. Okay. Then we have quick summary. You can read that, and we can move forward with our next chapter, which is architecture of our static keyword. Okay. Static nested classes and design guidelines. So in professional Java development, organization matters. Sometimes a class is so closely related to another that it makes sense to define one inside the other. So a static nested class serves this purpose without requiring an instance of the outer class. Okay. Static nested classes. A static nested class is defined inside another with the static keyword. Unlike an inner class, it does not need an instance of the outer class to exist. Okay. So we can use static nested classes when the inner class provides helper functionality that is logically tied to the outer class but does not need access to the outer class instance data. So inside this, you can do something like that. So here our node is logically part of our linked list, but does not need access to head or other instance data, right? And this is a clean way to organize our helper classes. And you can see this pattern throughout our JDK. We have quick decision guide, static versus instance, identify ownership, Does this data or action change for every object? If yes, then you can go with instance member. Okay. If no, then you can use with static. Then check dependencies. Does the method need to access non-static fields? If it needs instance data, then it must be an instance method. Otherwise, it should be static. Consider memory. If the value is constant, that will never change. Use static final to ensure only one copy exists in memory. And we will see this final keyword in our next chapter. Static versus instance comparison. Memory allocation, instance per object heap, static ones, okay, best for unique properties, share data, access via null reference, null pointer exception works, though not recommended. Always access with class name, right? We have quick summary part and we can move forward with our next chapter, which is our final keyword, okay?